Where does this missing piece come from? To help us understand what's going on in this puzzle, let's bring up a grid. Even in grid form though, we can see that as we rearrange these puzzle pieces, we still seem to end up with a missing unit square. Somehow the simple act of rearranging is giving us an entire extra unit of area. If we treat this as one large triangle, we can use our area formula 1/2 base times height, where the base is the 13 units along the bottom of this triangle looking object, and the height is 5. When we multiply that out, we get 32.5. But of course, if we have an entire missing unit, does that mean that the area of these pieces is actually 31.5? If we count up the area of the pieces directly, we get areas of 12, 5, 8, and 7. As we add those together, we get 32. So now we have 3 different possible measures for the area of these pieces. Which one is correct? If we actually draw in the diagonal, that would make a 13 by 5 triangle, and we zoom in, we can get a better sense of what's going on here. The diagonal doesn't quite touch the pieces the way that it should. In fact, there's some white space above it. If we imagine rearranging the pieces and tracking their edges, we would get this very thin parallelogram representing the missing area. When we rearrange the pieces, we can see that that parallelogram, thin as it is, supplies the entire missing unit square area. In fact, the problem here is we never had a single triangle at all. We had 2 different triangles with very slightly different angled edges. We can quantify that difference using something called slope. For the red triangle here, we can count up 3 units and right 8 units, giving us a slope of 0.375. For the blue triangle, we can count up 2 units and over 5 units, which gives us 0.4. 0.4, of course, is very close to 0.375, but is not the same thing. You might have noticed that the numbers involved in this problem, particularly these values on the bases of 5 and 8, are Fibonacci numbers. The Fibonacci sequence is a list of numbers in which, to get to the next number in our list, we add the 2 previous numbers. In this case, that would be 5 plus 8 makes 13. And Fibonacci numbers have several interesting properties. For example, among a set of 3 of them, if we multiply the first and the last, and we subtract away the middle number squared, we'll always end up with a value of either positive 1 or negative 1. This is called Cassini's identity. This identity can be used to construct a number of puzzles like this one. Imagine 2 rectangles, a 13 by 5 rectangle and an 8 by 8 square. We can construct some puzzle pieces that entirely cover the 8 by 8 square, meaning their area must cover 64 square units. But we can take those same puzzle pieces and appear to cover the entirety of that 13 by 5 rectangle, with an area of 65 square units. Once again, if we zoom in, we can see not only a little bit of extra space left over, but that very same parallelogram we were looking at earlier. When we rearrange our puzzle pieces back into their square form, it makes the missing unit square of 1.